Hi, Bobby.
Hello, Professor Aniruddhan.
How are you?
Good. So, what's the plan today?
Okay, so we have been teaching a lot of, AC phasor
Yeah,
analysis.
lagging, leading.
That's right.
Yeah, true.
We drew vectors and so on.
Mhm.
We should solve a few problems.
Ah. Otherwise, there were only equations last class.
Yes, that's right. So
Is
we
it-
need to solve a few problems.
Hmm.
I'm going to give you the hard part
Sure.
of suggesting the question
Okay.
because the answers may be easy, but making the question is much harder.
We'll start with something very simple.
Okay.
Maybe a voltage source feeding a capacitor.
Okay.
I wanted to know the current through the capacitor.
Okay. So something very simple.
Hmm.
I think we have done the analysis, but not with numbers.
Correct.
Let's do that. I think that's a good place to start actually. Okay, so now
We are very familiar with 50 hertz.
50 hertz,
So, but voltage will keep it low, not 230.
not 230 volts, yes. Many capacitors, we don't want them to apply to
Yes.
230 volts on the capacitor. Okay, so you said 50 hertz, right?
Yeah.
So frequency is 50 hertz, and which means omega is 2 pi f,
Yeah. 2 pi 50. Yeah.
2 pi into 50.
Yeah.
Radians per second.
Yes.
And what is the magnitude of the
Amplitude
amplitude of the
4
source?
volts.
4 volts. Okay, perfect. So we'll say this is 4 sin omega t.
Yeah.
Perfect. And what is the capacitance value?
Capacitance value should be some microfarad,
Some microfarad. Okay,
because that's what we usually see. So
that's true. Yes, yes.
for maybe some 0.318.
0.318. Okay, 0.318 microfarad. Perfect. Okay,
Just for ease of calculation.
just for ease of calculation. Correct. Okay, I understand. Okay. And what do we want to find? The current through the
We want-
capacitor.
yeah,
is what
current
you
through the
said, no?
capacitor.
Okay. So this is the current through the capacitor. I think by now people will be able to see the voltage across the capacitor is same as the input voltage,
Exactly.
4 sin omega t. And so clearly the voltage source value divided by the impedance of the capacitor, the reactance of the capacitor,
Reactance, yeah.
should give you the current.
Correct.
Okay, we just need to find out the magnitude and the phase.
Correct.
Okay,
So
maybe we'll start with this. So first thing I'm going to do is I'm going to say this 4 is sin omega t. I'll first give it some reference signs for
Yeah,
the,
yeah.
even though it's a sinusoidal source, it's changing direction. I'll say that 4 sin omega t is reference like this.
Okay.
Which means if I start with an angle, at some instant of time, I can imagine that this is higher, this is lower.
Yes. Yeah.
And everything is reference to that phase. Okay.
And
Which way do you want to do it? Should we calculate the reactance first?
We'll do that.
Let's do that.
Yeah.
So we said XC. In fact, JXC is the impedance, where
Yeah.
XC is the reactance.
Yeah.
I'll keep that here. So we said this is 1 over j omega c,
C. Yeah.
and this in this case, so 1 over j into 2 pi into 50 into the capacitance is 0.318 into 10 power minus 6.
Yeah.
Okay, so this is our reactance.
Yeah.
So 1 over j is minus j times, we need a calculator.
Yeah.
You have one handy?
Yes,
I see you have one
yes,
handy.
Yes, I have.
Yes.
2 into 3.14 into 50 into
0.318.
Yeah, it's close to 100.
Oh, okay. Very close to 100.
Yeah.
So 100, and then I have 10 power minus 6.
Minus 6.
So that would, so this is the denominator is 100.
Yes.
10 power 4. So
Yes.
10,000, I'll just call it 10 power 4.
Yeah.
And the unit will be ohms,
Yes.
reactance, right?
Yeah.
So minus, so one interesting thing I noticed, the impedance or reactance of the capacitor always seems to be negative. That I noticed, right? Because you have that 1 over j,
Correct.
it always leads to a minus j.
Yeah.
So if you just look at XC, it seems to be minus 10 power 4
Yeah.
ohms, right? Is this correct?
Yeah.
Okay. So this is something interesting to keep in mind.
Mm-hmm.
You have a capacitor, the reactance is negative.
Negative.
In some negative number ohms. Perfect. That negative most likely refers to the phase shift. No. Okay. Shall we use AC version of Ohm's law?
Yeah.
Right?
Straightforward.
That's straightforward.
Yeah.
So which form should we do it in? Rectangular form, basically A plus JB, or do you want to do it in phasors, or maybe draw the vectors? We should do all three.
Yeah.
Right?
Better.
Better to do all
Yes,
three.
Yes.
Let us do it in rectangular first.
Sure.
That's easy.
Sure.
So this 4 sin omega t is just 4.
4.
Right? So maybe I'll do it in 3 different colors. So let me do this. So this is 4 plus J0, right?
Yeah.
I'll just write it like this. We are just going to use 4. And we said this is minus J 10 power 4 ohms.
Yeah.
So this is 4 plus J0 volts minus J 10 power 4 ohms. So now in rectangular form, this current should just be 4 by minus J 10 power 4.
Correct.
Oh, this is very straightforward.
Yeah.
So this is basically 0.4 milliamperes
Yes.
with a plus J,
J.
right? So I am going to say 0 plus J 0.4 milliamperes.
Yeah.
I'll write it like this,
Yes.
right?
So it's
This-
leading.
It's leading the input
Voltage.
voltage. Input voltage was 4. This is plus J 0.4.
Yes.
So it is clearly leading. We
90.
saw this last time
Correct,
itself.
correct,
The
correct.
capacitor current
Correct.
leads the
Yes.
voltage applied across the capacitor. Okay, perfect. If you want to write it in phasor form, how will we write it?
Polar form.
Right, you're right, polar form. So this would be 4 angle 0. Okay, and this would be 10 power 4 angle minus 90.
Yes.
Angle minus 90. And then we would just write we just take the difference between, so we'd write it as 4 angle 0 by 10 power 4 angle minus 90, and this would just give us 0.4 milliamperes angle plus 90.
Exactly.
Right? 0.4 angle plus 90 degrees milliamperes.
Yeah.
Perfect. So this is very straightforward.
We'll just draw the phasor also.
We should.
Just
we
for
should,
the complete.
right? We should draw the phasor. So now 4 angle 0 is what we said, right?
4 volt.
4 volts angle 0. So this is 4 volts.
Yeah.
This is your voltage phasor, and the current phasor seems to be 0.4 angle plus 90.
Yes.
So I'll draw it like this. Like this. I'll draw it slightly shorter. So 0.4 milliamperes actually. And this is clearly a 90 degree.
90 degree. Okay.
Right?
Okay.
Perfect. So this is your voltage and this is your current.
Correct.
Perfect, good. We can see clearly in the phasors that your current is leading the voltage, and we are writing down the magnitudes and the units right there. Okay,
Right.
we need something more. That was quick, 5 minutes.
Yeah.
Maybe we'll do one more simple problem.
Yeah.
Mm,
Maybe some current source.
okay, oh, okay. See, last term we didn't see a lot of current sources,
Yeah.
so we should give a lot of problems.
Yeah.
Equal weightage to current sources. We'll do that. So this will be an AC current source. Okay. Some people like to put this also
Yeah.
for an AC.
Yeah.
Can you suggest and capacitor again?
Inductor.
Ah, okay. Okay, very good. What is the value of the, do you like to put this? Some people like to put that to show that it's an AC current source.
Yeah, I think it's
In
good.
some textbooks.
Yeah.
It's a good idea, right?
Yeah.
To distinguish
That is
between
less
DC and AC.
confusing.
Yes,
Yeah.
correct. Okay. And I'm assuming you're going to find out the voltage across the inductor,
Yes,
correct? This is
yes.
what we want to
Yeah,
find.
yeah,
Okay.
Yeah. Or even, yeah, correct.
Right,
Correct,
voltage
correct,
across the
correct,
inductor.
correct,
Okay.
correct.
What is the value of the current you want to
Current,
use?
let's take something simple, 1 milliampere.
1
peak.
milliampere peak. Perfect.
Same 50 hertz.
So 1 milliampere sin omega t. I'll write it in time domain form first.
Yeah.
So omega is 2 pi into 50. Oops. Right? And inductance value?
Last time we used 0.318.
0.318. That worked out nicely because
Yeah,
I got whole
yeah,
round
yeah.
numbers.
Maybe this time 0.159.
Point one. Oh, it's half of that. Okay, let's try it out. 0.159 millihenry. I think henries is too large.
Yeah, yeah.
Let's try to use millihenry. Okay. And we want to find out the current.
Current. Huh?
Okay.
Voltage.
Oh, sorry. We want to find out the voltage
Voltage.
across this inductor. Perfect. we know that we called it plus JXL, and that should be plus J omega L, right?
Yeah.
And okay, let's calculate what that is. Plus J omega is 2 pi into 50.
2 pi 50 is 314.
314, correct, 100 pi times 0.159.
50, 50.
50. So into 10 power minus 3. So 314 into 0.159 was 50, right?
Yeah.
So
49.9.
49.9.
Yeah.
So we'll say 50 J50 into 10 power minus 3.
Yeah.
Okay, into 10 power minus 3. And this again is ohms.
Yeah.
Interesting. So now I notice that the inductance, the reactance of the inductance is positive, right? So always we should expect, if the inductance has a plus J omega L, L is positive, omega is positive, it should always have some plus J times some number.
Correct.
Okay, great. Again, we'll do all three forms.
Yeah.
Let's do it in
Rectangular.
form
Yes.
first, right? So this would be 1 milliamp, 1 plus J0.
Exactly.
So we'll so it should be 1 milliamp plus J0. We need to remember that the current is milliamps. Okay. 1 milliamp plus J0 and times, so this one we said is plus J this thing. Okay, so this output voltage VL. So the voltage across the inductor is simply 1 milliamp plus J0, which is just 1 milliamp, times J 50 into plus J 50 milli.
Yeah.
Okay.
So it's
Milliohms.
50
micro, right?
Yeah.
So this seems to be plus J 50 microvolts, right?
Yeah, very small voltage.
Very small voltage. So it looks like, so it looks like in this case clearly the voltage is leading the current. So
Yes.
this was 1 milliamp.
Correct.
So that was the same as 1 angle 0, 1 milliamp angle 0. But this looks like this plus J has a 90-degree phase shift.
Yes. Yes.
Right? So you can write this as 50 angle plus 90. So microvolts, right?
Correct. Correct.
50 micro angle 90.
Yeah.
Right?
Yeah.
So it looks like it is leading the current, which
Correct.
is what we expect.
Which is correct.
Perfect.
We'll draw the phasor.
We'll draw the phasor.
Just for the visualization.
Just for the visualization. So in this case, the current
reference is current.
Reference is the current in this case.
1.
And 1 milliamperes. And our voltage was leading by 90 degrees with a 50 micro. So
Yes.
I'll draw that a little bit short.
Yeah.
50 microvolts, and this is 90 degrees. Perfect. Okay, that was again easy.
Yes.
2 5-minute problems.
Yes.
We should
So
go
if for example, if the frequency is increased by, let's say, 1000 times.
Okay, that's a nice question. So let's see what happens. If let me choose a different color.
Yeah.
So now what you're asking is, if omega were instead of 50 hertz, you want 50,000 hertz.
Correct.
Okay, let me see. So nothing will happen to the current.
Correct.
The impedance of the inductor seems to be going up at the same rate. Oh,
Yes,
this is
yeah,
very
yeah.
interesting. Okay, so if you had omega equals 2 pi into 50 into 10 power 3, 50k, right? Kiloradians per second.
Yeah.
Right? So this means, let's say XL prime. I'll call this XL prime.
Yeah.
So this is omega prime.
Yeah.
This will be 1000 times larger.
Yes.
So this will just be plus J50.
Exactly.
Oh, okay. Okay. So then the voltage would be now 50 milli.
Yes.
Okay, perfect.
At least some reasonable.
Reasonable number. Okay. So then this will be plus J 50 millivolts.
Yes.
Perfect. So nothing happens to the phasors if you just increase the frequency. The magnitudes of the phasors will go up or down.
Yes. Yes.
Right?
Yes.
Perfect. Perfect. Okay. That's very interesting. Okay.
So next, what shall we do?
Yes. Next, what shall we do? So let's add another source. So let's not jump to make it too complicated.
Yeah.
We'll add one more source, right? And actually you can do a lot, right? If you just take couple of sources, you can draw it in so many different ways.
Correct.
Right? Okay.
So 2 voltage sources?
2 voltage sources, okay, 2 AC sources, and you want to add a capacitor or an inductor?
Inductor.
Inductor, okay. So let's do that. Okay, I'm going to draw it like this. Now I'll take over the topology of the circuit.
Yes, please.
Let's say I'll make it like this. Basically, I'm adding them in series, right? All 3 of them in series inside a loop. This is okay?
Yeah.
Okay.
So that plus minus, do you want to indicate?
Yes, we need to indicate, right? So we'll say, I'm going to say, I'm like this.
Okay.
I'm going to indicate for this, and we'll of course want to find out the current through the inductor, right? Okay. And there is only one current in this whole loop.
Yeah.
So that's just I. Okay. So let us say the inductance, what did we use? 0.159 millihenry.
Yeah.
Okay. So maybe we'll choose something else. We'll use 0.318. It is giving us nice whole numbers.
Yeah.
So we'll say, actually, shall I just say, instead of saying 0.318 millihenry, I'll say 318 millihenry.
Yeah.
Right?
Yeah.
So I'm going to say that this is 318 millihenry. That's a large inductance. Okay. So we'll say 318 millihenry just for a change.
Yeah.
Most likely the current will end up being small. Right? Okay. And let us say a few volts amplitude.
Yeah.
So
2 volts.
2 volts?
Yeah.
Okay. So why not? So we'll use one of them as a reference. So I'll say 2 angle 0 for this. What shall we do? Let's say 2 angle 0 again.
Let's give same. Yeah.
2 angle 0, why not? If we do that, let's see what happens. So let me do one thing. I'll make some space here because we are going to need it. Okay. So, well, now that I've given the reference, I can actually do KVL around the loop.
Sure.
Right? So maybe I'll do that. I'm going to start from here, go around the loop and come back to this point.
Yeah.
Right? So if I do KVL, voltage increase, we'll take it as positive and voltage drop is negative.
Yeah.
So since we have taken the direction of the current, so we'll assume that there is going to be a voltage drop here, Vn, right? So 2 angle 0, so plus 2 angle 0.
Do you want to write it in polar or rectangular?
Rectangular. Shall we do rectangular? We might as well, because here it is just 2, right?
Correct.
So it is just 2 minus VL.
Yeah.
And minus 2 again.
Yeah.
Is 0. Oh, okay. It is just giving you inductor voltage of 0.
Yeah.
Right?
Correct. Oh.
It is giving me a voltage. Well, makes sense, right?
Both
so both sides are the
voltage.
same voltage, right? They are basically both sinusoidal. Each one of them is 2 sin omega t. The voltage across the potential difference is always 0. So this is a bad choice of, or rather, simple choice. Too simple.
Okay.
Too simple.
So we'll make some angle for one of the voltages.
We'll make some angle. Okay, good idea. Okay, I'll change this. Shall we make it 90 degrees?
Yeah.
2 angle 90?
Yeah.
Okay. So which means this was 2 sin omega t, this would have been 2 cos omega t.
Yeah.
Right? It would have been leading the
Correct.
sinusoid by 90 degrees. Okay. So, okay. So this definitely is going to give us a non-zero voltage.
Because there is a phase difference,
Phase
although
difference.
the magnitudes of the voltages are same.
Correct. Correct. So now this is 2 in rectangular. So if you do KVL between the same points, so plus 2
Yeah.
and then minus VL, and this is a voltage drop, 2 angle 90 is 2J,
Yeah. Yeah.
and this will be 0, right? So the voltage across the inductor is 2 minus 2J, right?
Yeah.
So 2 minus 2J,
2J.
perfect. So this is the voltage across the inductor. Now the current through the inductor will be
VL by
VL by J XL,
yeah,
right?
yeah.
And well, actually we should write down XL, right? So
Yeah.
let's write down JXL. I always like to keep the J's so that we understand, so that we remember, right? So J omega L.
So, this time also we are assuming 50 hertz.
50 hertz. Yeah, you're right. So 50 hertz. So we'll say F equals 50 hertz. So this is J 2 pi into 50 into 318 millihenry.
Yeah.
So 2 pi into 50 is 314.
Yeah.
So 314 into 318 is 10 power minus 3.
100.
100.
Yeah.
Oh, perfect. So plus J 100 ohms. Okay, makes sense. Okay, now I understand, because we got 50 milliohms there.
Yeah.
Plus J 100 makes sense. Okay. So then this current is easy. So 2 minus J2 divided by J 100.
Yeah.
Right? So 2 by 100 is 0.02. So this would basically give you minus 0.02 plus J 0.02. Is this correct? Complex numbers. 2 by J 100
is minus
J 0.02. Minus J2 by J 200 is okay. So it gives you minus 0.02 minus J 0.02. Right?
So
Amperes.
okay.
Amperes.
So
right?
suppose it was 0.02 plus 0.J02, then it will be 45 degree.
45 degrees. Correct. Correct. So this will be at some other, both are negative, no? That must be in the fourth quadrant. When the both real part and imaginary part are negative, most likely it must be in the fourth quadrant.
Okay.
Right? Let's see. So should we draw the phasors?
So that we have better clarity.
We have a better clarity, right? Okay, so let us do it like this. So 2 angle 0, that is our reference. So I'll draw it here. So this is 2 angle 0. I'll add that angle 0.
Yeah.
Okay, so just for reference, I got 2 angle 90. So that was like this, same magnitude.
Yeah.
So 2 angle 90. And we needed to subtract the 2.
Yeah.
So which means minus 2 angle 90 would have been like this, right?
Correct.
So this would be minus 2 angle 90.
Yeah.
Or 2 angle minus 90.
Yeah.
It is the same thing because it is just minus J2. And I want to take the difference between these two. So 2 angle 0 minus 2 angle 90 is the same as 2 angle 0 plus minus 2.
Yeah.
So that means I would have got
phasor.
Phasor here. So 2 root 2 angle minus 45.
Yeah.
Right? And that is actually VL.
So we'll mark that 45 degree there.
This is 45 degrees.
Yeah.
Okay. So 2 root 2 is 2.828. So it would have given me sine 45, cos 45, each of which is 1 over root 2. So yeah, 2 minus 2j.
Yeah.
Basically.
Yeah.
Right? That's what it is given. 2 minus 2j.
Yeah.
Okay, perfect.
So from this difference in voltage, current should be lagging by additional 90
Lagging by additional 90 degrees. Correct. So and then the magnitude will also get smaller by the reactance of the inductor.
Correct.
So this was 100. So the magnitude will be 100 times smaller, and in amperes units will also change. And you need to lag by another 45 degrees, right? Another 90 degrees. So that would be like this, minus 135.
Okay.
So this would 90 degrees. So this would basically be 2 root 2 angle minus 45. So this would be 2 root 2 by 100. So 0.02 root 2 angle minus 135. Is this correct?
Yeah.
And that's what we have got actually. So
Yeah.
the magnitude of this is 0.02 root 2 and both are negative. So makes sense.
So it's in the third
quadrant. It's in the third quadrant. Correct.
Oh,
This is correct,
nice,
no?
Nice, yeah.
So then if it is in the third quadrant, why is this minus j?
That's correct.
This is correct. So third quadrant, both are negative, right? Perfect. Oh, I think I made a mistake. I think I said fourth quadrant by mistake. Because both are negative, they have to be in the third quadrant. Correct. Perfect.
So suppose instead of 2 angle 90, suppose it was 2 angle 180.
Oh, okay. Okay. So let's try that out as well. We should try different phasors, right?
Yeah.
So to see what it gives. Okay. So 2 angle 180. Okay. We use the. Okay. 2 angle 180. Oh, 2 angle 180 is just minus 2.
Yeah.
Minus 2 sin omega
That
t,
is
right?
true. That's true.
So 2, okay.
Yeah.
Right? It will just be minus 2.
Yeah, it will be very
But
straightforward.
it will be very straightforward. But I think maybe we should draw the phasors.
Yeah.
Because that will be useful for them.
Yes.
So because this phasor analysis also is useful. So okay, let me make it a little bit shorter. So this is 2 angle 0.
Yeah.
And the second voltage is 2 angle 180. So this will be exactly same length but opposite side.
Yes.
2 angle 180 degrees. And this voltage VL
Is difference between
is the
these two.
difference between the two. So it will be 2 angle 0 minus 2 angle 180. So it will be double the length, no?
Yeah.
So I'll just show it like this. So this will be basically 4 angle 0.
Yeah.
So this is VL. And that makes sense.
Yeah.
2 minus minus 2, right? So 4 sin omega t, that will be VL. Now, which means the inductor current will be leading that by 180 degrees, which means it will be like this, and by 90 degrees, which means it will be like this, IL. It will be 4 by
100.
4 by 100,
Yeah.
so 0.04.
Yeah.
Angle 90.
Nice.
Perfect. So actually the phasor way of gives you some intuition, right?
Yeah.
On which direction,
Correct. Correct.
which is leading, which is lagging, and
It's a
if the,
very nice way of expressing.
that's right. That's right.
Yeah.
Correct. Perfect.
Yeah.
Perfect. Okay. So this was very straightforward. I think maybe we'll give them more practice problems and activity problems during the week.
Yeah.
Most of it is very simple complex analysis. Whatever they did with DC sources and resistors, they are now doing it with ACs and complex numbers.
Yeah.
Perfect.